From towering mountains to the gravel and pebbles along a river, Earth's solid exterior is made of a huge variety of rocks. Some are even being formed this very moment as active volcanoes spew lava that hardens as it hits the atmosphere or ocean. But most of the Earth's rocks are extremely old. Each rock is a shapeshifter, shifting form over time with a history that can span millions of years. And here's what geologists and rock climbers and your aunt with a collection of heart-shaped rocks know that lots of us overlook. One rock is not just like any other. I'm Alize Carrere, and this is Crash Course Geography. Way back 4.5 billion years ago, when the solar system was forming, the Earth solidified as a swirling nebula of dust and gas that collapsed under its own gravity. Then, as gravity kept pulling on different molecules, the Earth formed its spheroid shape made up of different shell layers. In fact, even though we sometimes think of it as being separate from the Earth, the atmosphere is really the first and lightest shell with its own set of layers. At the bottom of the atmosphere, things start to feel more solid, and we hit Earth's crust. Compared to the rest of the planet, the crust is extremely thin and has a low density, which is how tightly packed the molecules are that make up something. Particles in the original gas and dust that ended up in the Earth's crust became the minerals, or inorganic naturally occurring chemical compounds with a crystalline structure, and rocks, solid collections of minerals that we find on the planet today. There are actually two types of crust on Earth: continental crust and oceanic crust. Continental crust makes up the major land masses on Earth that are exposed to the atmosphere. It's made of light-colored and lightweight rocks rich in silicon and aluminum, which help make it the least dense layer besides the atmosphere, but not the thinnest. That would be the oceanic crust, which is what forms the vast ocean floors. Oceanic crust is made of heavy, dark-colored, iron-rich rocks that also have a lot of silicon and magnesium. It's denser than the continental crust, but only a few kilometers thick. Beneath the crust is the much thicker mantle. It stretches for roughly 2,900 kilometers and is rich in elements like iron, magnesium compounds, and combinations of silicon and oxygen called silicates. The mantle is so thick, it actually gradually changes density as we go deeper into the Earth. The lower mantle is closer to the center, where pressure is higher, so it's denser as everything is pushed together more. The last layer in our journey to the center of the Earth is the core, made of iron and nickel. The 2,400 kilometer thick outer core is so hot, all that iron becomes molten and turns to liquid. But the hot, dense inner core of iron with a radius of 960 kilometers is always solid because of the tremendous pressure. No one has been to the center of the Earth, but scientists study how seismic waves from earthquakes travel through the planet to model the Earth's interior. And learning about what Earth is like on the inside helps us learn about earthquakes, volcanic eruptions, how continents formed, and even about the origin of the planet itself. Some of the elements show up a lot, but each layer has a distinct chemical composition and temperature, and each one in its own way helps give us the rocks and landforms we see on the surface. Like here, high in the Himalayas, where a large chunk of granite is newly exposed on the surface. During the day, its grains glint in the sun, and as night falls, the rock blends into the darkness. An occasional goat clambers on its rounded dome, searching for a tuft of grass. It seems innocuous enough, but seeing granite here means that at some point in time, eons ago, volcanic activity was transforming the surface. Within the Earth's crust and beneath the surface is magma, or molten rock, that can cool and solidify into igneous rock. Igneous rocks make up about 90% of the Earth's crust, though you might not notice because they're often covered by other types of rocks, soil, or ocean. We actually end up with different types of igneous rocks depending on whether magma cools above or below Earth's surface. When magma cools and solidifies beneath the Earth's surface, it forms intrusive igneous rock. And granite is an intrusive igneous rock. But when magma erupts onto the surface, we call it lava. And after it cools and solidifies, it becomes extrusive igneous rock. There aren't any volcanoes in the Himalayas, but 60 million years ago in the initial Himalayan mountain building phase, volcanic activity like magma churning beneath the surface would have been common. From measuring the magnetism of rocks, dating plant and animal fossils in the rock, and studying the changes in how land moves, we know the Himalayan mountain ranges formed when the Indian and Eurasian plates, or chunks of crust floating independently over the mantle, collided. And this process still continues today. Around 60 million years ago, the Indian plate was about 6,400 kilometers south of the Eurasian plate. As it moved north, an ancient ocean called the Tethys Sea was dragged down beneath the Eurasian plate into the Earth's interior. The oceanic crust and all the tiny sediment particles that used to be on the shore of the sea were also dragged down where they melted into magma. Eventually, the magma moved into cracks and fissures deep inside the Earth, where it solidified into our granite. If we brush off some of the dirt and grass and ask that goat to move along, we can get a better look at our rock and its texture. Rocks contain minerals that form crystals, which is when molecules or atoms are arranged in a regular repeating pattern. How fast magma cools affects crystallization and the texture of a rock. Intrusive rocks, like granite, cool slowly, so they have more time for larger mineral crystals to form, which is why granite looks coarse-grained and we can even see the crystals without a microscope. Magma can also occur at different depths within the crust and mantle, which means it's exposed to different temperature and pressure conditions too. Heavier minerals deeper down will crystallize first and be denser and darker, while minerals that form closer to the surface are less dense and lighter in color. So our granite is felsic, which means it's rich in light-colored, lighter-weight minerals, especially silicon and aluminum, and the magma that it came from was closer to the surface. On the other hand, lava cools very quickly when it hits Earth's surface, which limits how crystals grow. Extrusive rocks like basalt end up with small individual minerals and a fine-grained texture that looks much more seamless. And basalt is mafic, which means it's rich in darker, heavier minerals like compounds of magnesium and iron. Even though it formed from lava on the surface, the original magma was deep in the Earth's crust or mantle. Yet somehow, our chunk of granite made its way to the surface. Like maybe it was uplifted as the Indian plate pushed further north and as the Himalayas rose. At the surface, rocks have to deal with different temperatures and pressures than where they formed deep within the crust, not to mention weathering and erosion, or being broken down by the Earth's atmosphere, water, and living things. Water, with its ability to dissolve practically anything, can especially alter, disintegrate, and decompose rocks. The pieces can then be picked up and deposited elsewhere. So once the extra rocks and soil are removed by weathering and erosion, our granite is exposed to a totally new surface environment. And it might seem like the granite outcrop is just sitting there doing nothing, but unseen processes are operating. Like the pressure is different out here on the surface, so the outer few centimeters of the rock might expand outward and crack. Then the loose outer layers of rock can slough off, like a snake shedding its skin. Or temperature differences can also cause the rock to expand or contract. This leads to granular disintegration, or when individual mineral grains break free from a rock, which is how over thousands or millions of years, tons of little rock dust pieces accumulated around the base of this granite boulder. So as clouds gather over the mountaintop and a steady rain begins, the little mineral grains can get washed into a stream and may eventually be dropped along the channel banks during a flood. Or they'll bounce along with the water and travel all the way to where the river empties into the sea, and the grains become part of the ocean bottom. Grains like these are sediments. Centuries of monsoons and soil erosion have blanketed the floor of the Bay of Bengal in up to 20 kilometers of sediment from the Himalayas. So part of our granite boulder is actually lying on the bottom of the ocean. If we could slice into all the sediment lying on the floor of the Bay of Bengal, we'd likely see horizontal layers or strata from different times when large amounts of sediments were deposited. Over time, the pressure from the weight of the material above compacts, cements, and transforms the sediments into sedimentary rock, which still shows some of the original layers. So sedimentary rock like sandstone is made of cemented sand-sized particles of quartz and other minerals. It has very visible grains, lots of tiny little holes, and is very resistant to weathering. Other sedimentary rocks like limestone are formed when the remains of organisms like shellfish, corals, and plankton sink to the ocean floor. Coal is another one of these organic sedimentary rocks that's created when organic matter accumulates and compacts in swampy environments over millions of years. At the bottom of the ancient Tethys Sea, which disappeared about 20 million years ago, sedimentary rocks would have formed from sediments brought down by rivers. But as the Indian plate pushed northward, the gap between the Indian plate and the Eurasian plate narrowed. As the plates collided and the Himalayas formed, the sediment on the seafloor was compressed and crumpled. On top of being squished and crumpled, the rocks also have to go through intense temperature and pressure changes. All this action causes the existing rock to go through metamorphism and change into a completely new rock type. All the minerals from the original rock recrystallize without having to melt down into molten rock. The new metamorphic rocks are typically harder, more compact, and more resistant to weathering. So if any sediment from our chunk of granite got caught up as the Tethys Sea was sucked under, it would probably change into gneiss. Gneiss has alternate bands of light and dark minerals and can form from a variety of different rocks. It's also very hard and resistant to weathering and erosion. So our granite boulder started life as igneous rock. But as pieces broke off, they could have been compacted into sedimentary rock or changed into metamorphic rock. It seems like it's sat there for all of time, but rocks like our chunk of granite are continuously altered over millions of years from one rock type to another as a part of the rock cycle. But the story of our granite is not the story of all rocks. There are many pathways through the cycle. Like igneous rocks could skip being sedimentary rocks and go directly to being a metamorphic rock, or even remelt and recrystallize to make new igneous rock. Whether scaling a 3,000-foot high granite monolith or kicking a pebble down the road, each piece of rock has a story that may be millions of years old, etched in the stone by processes both on the surface and deep within the earth. Next time, we'll tell the stories of another kind of shapeshifter, continents, and how plate tectonics have created the Earth we know today. Many maps and borders represent modern geopolitical divisions that have often been decided without the consultation, permission, or recognition of the land's original inhabitants. Many geographical place names also don't reflect the indigenous or aboriginal people's languages. So we at Crash Course want to acknowledge these people's traditional and ongoing relationship with that land and all the physical and human geographical elements of it. We encourage you to learn more about the history of the place you call home through resources like nativeland.ca and by engaging with your local indigenous and aboriginal nations through the websites and resources they provide.